Welcome back. The objective of this video is to introduce simple harmonic motion, and we'll write sinusoidal functions with harmonic motion. As a matter of definition here, an object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin, d, at a time t is given by either of these two functions. D equals a cosine of omega times time, it's a lowercase omega there, and d equals a times sine omega times time. The motion will have amplitude, which is the maximum displacement of the object from its rest position. The period of the motion is 2 pi over omega, where omega is greater than 0. And the period gives the time it takes for the motion to go through one complete cycle. So very similar to what we have done previously. And then frequency, the motion will have frequency, and frequency is the reciprocal of the period. It's omega over 2 pi, and that's the number of oscillations per some unit of time. So example 3 here says a point on the tip of a tuning fork vibrates in harmonic motion described by the equation d equals 12 sine omega times t. Find omega for a tuning fork that has a frequency of 386 vibrations per second. So all we want to do is find omega. Well, our frequency here is omega over 2 pi. That was more of a W, but we'll go like that. And that equals 386. And we want to solve for our numerator here. So if we multiply both sides by 2 pi, the 2 pi cancels, because I multiplied this side by 2 pi, and I get W equals 386 times 2, and I called it W, I need to call it omega, and we get 772 pi, and that's radians per second. In example 4, a ball on a spring is pulled 6 inches below its rest position and then released. The period for the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. So what I see here, I see our midline or our x-axis would be rest. And if we pull this spring 6 inches below the rest position, we're going to start at a -6. So this is a little bit like a negative cosine curve. So I'm going to use the cosine formula for harmonic motion. Second, since our period is 4 seconds, for the period for the motion is 4 seconds, we can solve for our omega, right? So 4 equals 2 pi over our omega, and in solving for our omega, we get omega equals 2 pi over 4, or pi over 2. So then our function becomes d equals -6 cosine of pi over 2 times t. So that -6 is our amplitude to start, and we'll go through an entire cycle in 4 seconds, and our curve will look something like this, where our maximum will be +6, and that will occur at 2 seconds, and our minimum will again be at -6. In example 5, it says a mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, can be modeled as harmonic motion. If the weight is displaced a maximum of 4 centimeters, find the modeling equation if it takes 3 seconds to complete one cycle. Assume the object starts at rest. So if we start at rest, we'll have a midline at y equals 0, or our x-axis. And so if we're starting at rest, we're going to start at our origin, and I would use sine. Second, we know that if the weight is displaced a maximum of 4 centimeters, we know our amplitude is equal to 4, and it takes 3 seconds to complete one cycle, so then our period is equal to 3 seconds. We'll complete an entire cycle in 3 seconds. So completing a whole cycle will reach our back at midline halfway through, and we'll finish and our maximum of 4. Our curve will look something like this, and a minimum of -4 at 9/4 of a second. So now we can write our function. Although we do need to figure out what our value of omega is using our function for period. So 2 pi over omega is equal to 3. We multiply both sides by w and divide by 3, and we get 2 pi over 3 equals our omega. So we're going to use our sine curve and write our function, and we get d equals our amplitude of 4 sine of 2 pi over 3 times t. Example 6 is a Ferris wheel question. A Ferris wheel is constructed such that a person gets onto the ride at its lowest point, 5 feet above the ground, and the ride reaches its highest point at 125 feet above the ground. So we're going to go a total of 120 feet. The amount of time it takes to complete one full rotation is 8 minutes, so the whole rotation takes 8 minutes, so we'll reach our highest height halfway through at 4 minutes. The vertical position of the rider can be modeled as a function of time in minutes since boarding, using the equation y equals a cosine of b times t minus c plus d. So we're using a cosine curve, so we're starting at a height of 5 feet, and it takes 8 minutes to return to that height of 5 feet. So we will finish here at 5 feet. Halfway through, we will be at a height of 125 feet. So we've got 3 of our 5 critical points. What we need to do is to find our midline. So our midline is going to be 60 feet, because we go a total of 120. 60 feet, we're going to split the difference here, and our midline is going to be at 65 feet. So I put my midline in at 65 feet, right, an amplitude of 60 above the 5 and 60 below our maximum. So we've got our midline. And then our halfway time was 4, and half of 4 is 2. So we'll be on our midline here at 2 minutes. We'll reach our midline of 65 feet. And at 6 minutes, we'll also be again back down at 65 feet. So putting our ordered pairs in and our 5 critical points in our midline, and then sketch our curve with our changes in concavity at the midline. Using our equation a cosine of b t minus c plus d, we're asked to find the values of a, b, c, and d. Well, a is our amplitude. Hopefully that's pretty easy. We see we've got an amplitude above our midline of 60, so our amplitude is 60. D, that's going to be our midline. Our D is 65, so we've shifted our 0 line up to 65. And then there's no phase shift here. We don't have a phase shift, so C is equal to 0. And then finally, probably the toughest one to find is B. Our period is 8 seconds, so 8 is equal to 2 pi over b, so we're not doing harmonic motion anymore. And let's go ahead and solve for b. So So multiplying both sides by b and dividing by 8, we get b is equal to 2 pi over 8, or pi over 4. In C, we're finally able to write the equation that models the function, which is y equals, and this is a negative cosine curve, so our amplitude is 60, but our a value is negative 60. So I probably can correct that up here. That should be a is negative 60. And the cosine of pi over 4, t minus 0, and then plus our midline of 65. And in question D, at what time is the rider 65 feet above the ground? Well, the rider's 65 feet above the ground at 2 seconds and 6 seconds, and will be there every, 2 minutes and 6 minutes, and every 4 minutes thereafter, as long as they're still on the ride. So at 2 minutes and 6 minutes, or at 2 plus 4t and 65. That probably shouldn't be a t. It probably should be like 4n. And that concludes our introduction to simple harmonic motion and writing equations. And we'll get some more practice with this when we see you in class.